Go live. And we're live. Okay, hello. This is the 4th episode of Scripting for Noobs with Leandro up there. Yes, up there. I'm pretty sure up there. And yeah, today we're looking at JSFX. So that's going to be fun. We're going to try make hopefully like a simple effect just to kind of get an overview of what scripting in JSFX will look like. I'm passing the mic to Leandro.
Hello everyone, I am Leandro Facchinetti. I have a channel in which I talk about programming and sometimes about ReaFir. So I have developed ReaFir scripts and JSFX and also some JavaScript stuff, all sorts of different front projects. And I have the pleasure of being here today. Thank you for having me over, Arya, and we will write some JSFX.
Yeah, sounds fun. Oh, hello, Bo. Thanks for joining us. I'm somehow hearing a copy of our live stream on here. Are you hearing that?
I am not hearing that, but maybe you don't have the YouTube Studio on mute.
Oh, yes, that's what it is. Oh, this is muted. Oh, okay. It's I think here. Dumb. Yeah. Okay. Here we go. Fantastic. There's always got to be something to start kind of shaky when you're on the old IDDQD sound. So Leandro, with JSFX, I know we're dealing with a new language, but maybe you can, just tell us a bit about the language.
So we have been streaming so far, writing Lua scripts. So they are the kinds of things that allow you to move items around or create tracks. Basically, do the kinds of things you would do by clicking around in ReaFir. And those scripts are written in Lua. It's a programming language that you can use in several programs. You can use Lua in ReaFir and in OBS and Hammerspoon. Well, several of some Lua code. It's a programming language that is relatively easy to learn and to use for all kinds of things you would like to do in all these different programs I mentioned. And then we are now going to write JS effects. They are real-time audio effects or video effects, but I don't think we are going to touch on that. So they are real-time audio effects, and processing real-time audio is a difficult task. I mean, there are 48,000 samples per second on a normal sample rate, or 44.1 thousand. So like a lot of numbers to crunch. And if you tried to do that using Lua, you could run into issues. There are some projects that try to do real-time processing of audio in Lua, but they don't seem to be maintained anymore, and I have never actually tried to use them. I don't know how good they are. So computing real-time audio is intensive. It's a lot of work to do. So the developers of ReaFir came up with this language that is super limited. You're not going to find this language in other software, and it doesn't allow you to do any kind of computing that you would think of the same way that you can do in Lua. No, it's a purpose-built language for processing real-time audio and video to some extent. I think that the language was actually designed to work with video in Winamp. If you don't know this, there's a bit of lore. The creator of Winamp, that old media player for Windows, is the creator of ReaFir. So the language, I think, was just ported, and the first version of the language, EEL, was for Winamp to do. Remember those visualizations? You were listening to some music, and then you could see like colors and flashy lights. So you would write those effects in EEL, and then later, when Justin was developing ReaFir, he ported the language and improved on the language. It's called EEL2 now. And it's a language that allows you to write real-time audio effects, which is awesome. As far as I can tell, and I did a lot of research on this, there are very few competitors to this. There are very few languages that allow you to do real-time processing of audio in a way that is high level. It's relatively easy for us to understand code in EEL2 as opposed to languages that would traditionally be used for this task, like C and C++. So it is quite unique, and it's also portable. If you write some effect in ReaFir in Windows, it will work in macOS and Linux for the most part, which is not true of C and C++ for the most part. And of course, there is the trade-off. You are tying yourself to ReaFir, so if you write an effect in JSFX, you will not be able to use that in Ableton Live or Logic. So it is a relatively easy language to learn in the sense that it is rather small. There is not a lot for you to learn, but the downside is that it's a small community around the language, so you will not find a lot of resources to learn besides just a couple pages on the ReaFir website, and that is pretty much all you get. So there are a few other resources. Aria and I have collaborated on a video, and I linked to other resources there, but there isn't a lot, and it's mostly just playing with numbers, and you have to know what to do with the numbers. The language comes with very little help in terms of libraries and things you can use. So there is no let's pass an EQ here or a compressor there. No, you just get a bunch of samples, and you have to come up with the idea and the logic for a compressor and an EQ yourself. Yeah, so that's the spiel on JSFX and EEL2.
Yeah, that's cool that you mentioned about Winamp's those visualizations, because those, I miss those, and I would love to. Do you think like would it be possible to eventually, not today, but eventually make something like that, so you would put something on like your master bus, and in the video window it shows you like visualizations or something like this? Oh,
that
cool.
already exists, yes. So the way it works is you have to collaborate with two different plugins. You have to have a JSFX to capture the audio and then send the audio to a video processor. And then you can write a video processor, which is similar to, but not exactly the same as, an audio processor. I mean, a JSFX and a video processor are both written in the same language, EEL2, but they have different APIs and things that you can do with them. And in general, the way that you write is different.
Cool.
Different controls for the user input and everything. It's similar, but not quite the same. So you write a JSFX that sends audio to a video processor, and in your video processor, you capture that audio, and you can just play around with pixels. You can do whatever. So there is already in ReaFir, it comes with ReaFir, there is a JSFX that sends audio to a sample. So when you put a video processor in a track, there are all these presets you can choose from. And one of the presets is one kind of visualization. I think it's like a circle that reacts to the song.
That's dope. And also, sorry, go on.
And by the way, incidentally, that architecture is also how I developed one of my plugins. It's an auto mixer, which is something that you may want to use if you have a room with many microphones open. So you can imagine an interview or a conference, that kind of setting. And the auto mixer does, it mixes the microphones, the audio portion of that. But there is an extension that I wrote that allows you to take if you have several microphones in a room, but also several cameras. So now we can imagine that there is a round table and cameras pointing at different people. You can set up a video processor that is an auto mixer, and what it does is it switches to the camera of the person who is speaking. So that's something that Zoom does when you're on a call, or I guess Skype does that as well, but it's not something that you usually see on post-production. You have to do all the scene switching by hand. And using the auto mixer, you can do that automatically. And it's based on this architecture. So I have in the auto mixer, the audio portion, I send a bit of information. I don't need to send the whole audio. I just send a bit of information, which is who is speaking right now. And the video processor picks up that information and renders that video source.
Yeah, that's super useful because, yeah, I think in post, and especially like even if you have like a Zoom live stream or something, you're still hopefully like having people record their own audio and video separately and then mix that in post. So this is a really cool system. Super dope.
Yes. I mean, I had some people using it or trying to use it on more professional settings. And it is good that it is super fast to use. You can come up with a rough cut in, well, in no time. You just have to drop in all the media sources in ReaFir. But I have feedback that it doesn't work as well as it could. And I'm working with the person to work on all the small details to make sure that all the transitions look good and everything. So it's not like 110% yet, but it's good enough. I have used it.
It's in the beta phase, I guess. Here, you need users to kind of see.
Yeah. If you try it out and you don't like the way it looks, then please send some sample ReaFir projects that I can look at and I can try to come up with something.
Cool. Yeah, I can also, if you need help testing it, I can also be available for that. So yeah, so from what I understand, and you figured out how to fix this, but we can use the same environment as Lua scripts, like the same development environment. We can use it for JSFX, but I remember you could go to edit JSFX and it would open that, but now it opens a text editor, and you figured out a way of opening it not in the text editor.
Yeah, it's rather simple actually. You just drop the effect in any track or any media item or whatever. Drop the effect somewhere, and then open the window to control the effect and go to edit. Cool. Opens up. This is one of the coolest things ever. This editor it looks kind of crappy, and that's okay. But what is super cool about it is the right pane. In there, you will see all the variables in your program and all the variables given to you by ReaFir in real time, which is like amazing stuff. If you are developing audio effects, you'll be crunching numbers and you'll have to do a lot of crazy mathematics. So having all these numbers on the screen at the same time is just remarkable. I don't know if of any other thing that does that, but at the same rate, I am no specialist in developing audio effects with C and C++. So maybe something already exists that looks like this. But this is awesome.
That's very cool. And what is this R? Trying to expand this, but it never. Oh, okay. Like how many times it's referenced in the project? And the value, is that like a floating value? Like if I play something, will that value change constantly?
It depends on the effect, because these variables that we are looking at here are the variables in this effect, and I don't know how this effect works. So I suppose that these values will change, but I know for sure that the system variables, you can see below there is a cut on the right-hand side pane. There is a cut and it says system variables, and you can see all the variables that are given to you by ReaFir, and those will definitely change if you pass some audio through this effect.
Cool. Yeah, so how do we start?
Well, I think we need to start with an idea, and we had the idea of a game, we had the idea of a delay. Bo, who is watching us right now, wanted me to do an EQ, and an EQ is kind of a good first project because it's rather simple, but the other projects are also fun. I don't think we would be able to complete them in one session, but we could get started. So how do you want to go? Do you want to go with something rather simple but kind of cool, like an EQ? Or do you want to go for something that is more sophisticated?
No, yeah, I'm down for EQ, especially if Bo is down. I actually have a couple of EQ ideas. One would be like a way of kind of testing yourself, where you put an EQ on a track, and then you close your effects window, and the EQ would randomly cut or boost a band. And it won't be like a very specific thin band. It would be like either I'm cutting or boosting 20 to 200, or 200 to 1K, or 1K to 10K, or 10K to 20K. And then it somehow like remembers the last move it did, so then you can go and check.
That sounds like a fun idea. It's a mix between an EQ and a gain.
Yeah, exactly. Yeah, and you can like kind of practice your EQ, like your ear. Train your ear. Jesus, I can't speak today because of the heat wave. Yeah, so let's start. Yeah, if do you think if that's straightforward enough and can teach a lot to beginners, I think that would be a good idea.
Yeah, EQ is just one of those things that you have in every single track ever. So it's like a fun first project, and it's not something that I have already covered in my channel because I don't want to repeat content. You can go over to my channel and browse through some older videos. I have live coding sessions for many audio effects, like some simple stuff like a white noise generator, some stereo manipulation, but I also have a code review of the auto mixer, which is more sophisticated. So you can go there and watch all this content already. So let's do an EQ. So how about we start with closing this window because we don't need anything from there. Click somewhere in the effects window and you'll be able to create a new JSFX.
Oh, cool. Right here?
It is where you select effects.
Oh, in the FX browser.
Yes.
I don't have empty areas, but let's see. No. Come on, give me an empty area. No. Oh.
I guess it may.
Oh, create new JSFX.
You may write.
Yeah,
there you go.
Okay. So
there
you click anywhere
so let's
on
create
this
a new
pane, I guess, and you go create new JSFX, and we'll call it Leafac IDQD Bo Bops NY EQ random EQ. Let's just call it for now. Okay, and we get a thing like this.
Yeah, so click on edit, and we get sample code to get started. And I suppose we can just read what is in there and start modifying stuff.
Okay.
And understand how you organize your code. So to begin with, these first lines are a high-level description of what's going on. This desk line is what is going to show up in the effects browser. So right now, if you go to the effects browser, you will not find Leafac, IDDQD, Bo, Bob's new eye. No, you will find new effect. And if you don't have a line that reads like that, then it will pick up the file name. In my effects, I usually don't have a description like this. I just let it pick up the file name, but it's up to you what you want to do.
Cool.
Then, but we definitely want to change the description if you're going to keep it. And I don't know about that space right after desk. I don't know if it will remove the space or if a space will show up in the browser. So, and I think that we should probably sign there as well. So you would say Leafac IDGQD Bo Bob's new eye, right? Because we want that to show in the browser.
Yeah, and this is a regular string. Like if I put forward slashes and stuff like that, that wouldn't. Yeah.
Anything goes there. So now save this and go to the browser, and we should see the new effect there.
Cool. I'll go to JSFX, and well, I'll just search for it. There it is.
There it is. So the next line is this slider line. So when you're writing JSFX, you have a limited number of controls that you can put in these sliders. So usually when you open a JSFX, you'll see a bunch of these sliders. unless the person is going fancy and drawing a user interface, which is something you can do, but it's rather advanced. And if you're writing a good user interface, most of your code will go into the user interface and most of your bugs will be in the user interface. The audio portion is usually a lot shorter, but there is more mathematics involved, so each portion has its complexities. But usually, if you can do something with just the sliders, that's usually better. And I don't know yet how we are going to structure our EQ, so I don't know which sliders we are going to use. But if you want a slider to appear in the window, this is what you write. You write slider number, and you may have up to 64 sliders. So you write slider 2, it will be the second, and then you give it a name. This name is not what's going to show up in the user interface. It's the name of the variable that you're going to use to refer to this value in your code. So it's one of the things that will show up on the pane on the right. It's one of our variables. You can see that already gain dB is there. No, it doesn't seem to be there. But slider 1 will be under system variables. You can scroll down and you'll find slider 1. And that's another variable name. You can just use that if you don't want to use gain dB. And there is our 0. And if you slide on the interface for the plugin, if you slide, you'll see that number change. So yeah, the name of the variable, and is the value not changing?
No, but I'm wondering, is it because, like, if I press edit again, will that change? No.
Well, that value will change at some point in the future.
Cool.
Trust me. So you have the variable name and then an equal sign and then the default value for that variable. So when you load the plugin, what is the value of that variable? And then you have to put in the angle brackets, however you want to call this, less than, and then now you specify the range. So this value will go from, well, I guess it's a dB value, so it will go maybe from -60 to, or do you want to not boost that much?
Yeah.
-60 up to 12 maybe?
I was writing
So you can
this
write
for Q. I'm just gonna write this for gain 2 or something. So that, yeah, we just use dB values. Yeah, let's do, so can you, if you want to do minus infinity, do you just gotta go like -300 or something for that to work?
Yep.
Cool. And yeah, maybe we can. This is the cool thing with JSFX, is that if it only goes up to like +12, you can just modify it to go up to like 18. And then the last one is increments, right?
Yes, the last one is how much you want this to increment when you slide. So as Arya was saying, you can always edit the source of an existing audio effect to change its range. But you can, because this is just a simple slider, in the interface, you can double click on that box that says -47 right now, and you can put whatever value you want, even if it's out of range and even if it's not in the right step. So if your step is maybe 1 and you can only go increments of 1, you can put something fractional there and it will work. So now that's the step, and maybe we go like 1 at a time, 1 dB at a time. And then you close the bracket, and then you can give the name that will show up in the interface.
For now, let's just do this.
And then save.
Boom.
And then you see a new slider.
So why did it do now, 1 now when we said the default would be 0?
For some reason, you can see on the right pane that all the sliders we have not declared, so you can see slider 2 onwards, they are all value 1, and I have no idea why. But if you remove this effect from the track and drop it again, the value will be 0. Or alternatively, if you double-click on the bar, if you double-click on the slider, it will reset to 0. So yeah, that's another thing we should talk about. And I should probably have mentioned this first. what is the first thing that you do when you start developing a plugin? You mute the audio. You mute the audio. You don't want to blow up your ears. You mute the audio. When you are developing things, you will probably create a lot of noise and blow things up because you're just playing with numbers. And if you mess up with the numbers, you will create a lot of noise. So mute the track that you have your effect in. And when you are developing and you're changing the effect and you save, ReaFir will update the execution in real time. So if your sliders are in a certain way and you add a new slider, the new slider will be in no man's land. And that's what just happened. So if you have a slider that is supposed to go from 0 to 0.0001, and then you save, and then all of the sudden it is at 1 by default for whatever reason, and you're blowing up your speakers because of that.
Good point.
Yeah, you can get hurt while doing this. What I usually do myself is I mute the track, but I also remove my headphones.
Like double.
When I'm developing an audio effect. Yep. It's smart to use one of those big headphones that you can just put down, and it is safer to do that. You don't want to damage your hearing. So yeah, a couple pro tips about sliders. These are things that you're probably not going to run into the first time you're playing with this, but it's interesting to know. If you put a number that is not consecutive, so it's not slider 1 and 2, if you put any number from 3 onwards, it's going to put a small space between the sliders on the interface, which is helpful if you want to group certain sliders together.
Cool. So if I, for example, just copy this and call it like slider 4 and call it gain 3, that would go a little cool with a little space. And I guess if I make this 5, boom, it goes a little further. Oh, it doesn't.
No.
Oh, okay.
It stays the same.
I was wondering about that. Interesting.
Yeah. And another cool trick, there are several cool tricks about these sliders. The next one is if you want to have a slider that you don't want to show to the user, you can. And this slider may be helpful if you want to have like an advanced option that most people will not have to touch. I do something like this in the auto mixer. There are plenty of options that most people will never have to touch. So I hide the sliders. They're still there. If you go to, so let's make the gain 3 slider disappear. So you can put a minus right after the close bracket. So it will read minus gain 3.
Okay. Like this?
And then you save, yeah, like this. And then save, and the slider doesn't show up anymore. But it's still there. So you can go to param on the effects interface, and you can go to effects parameter list, and then you can, for instance, show in track controls. So you can still see gain 3 there, and then it will show up in the track control panel. And that's something that you can do. Another thing you can do is you can have drop-down menus. So maybe your options are not a slider. They are just different modes of operation. They are maybe different presets, something like that. So you can have a drop-down if you want, and then it will behave as a slider of step 1. So you will go from, it will still look like numbers in your code. So it will be like 0, 1, 2, and 3, and so forth. But you will be able to give a label to these numbers so that the user can select between the labels.
One quick question from Bo, and hey Bops NY, hello. But yeah, Bo asks, I'd love to see how you'd code an EQ based on a Hall moving average. I don't know what the Hall moving average is. You probably do. Oh, okay.
I don't.
Well, we can Google this. Let's just do a quick Google. Hall moving average. Sounds mathy. Hall moving average is a directional trend indicator. Oh, okay. It captures the current state of the. Okay, yeah, I see. So the way this would apply in EQ would be that if you have like kind of like a parametric EQ where you have like 100 different sliders and then like kind of drawing a line between them.
I don't think that's it though. Okay, so do you want to jump ahead and start talking about the mathematics of this effect?
Sure, yeah.
Okay, so stop JSFX, let's talk numbers. In the end of the day, what we are going to do is manipulate numbers. The samples are numbers. And we need to manipulate these numbers in a way that makes sense sonically. So these numbers are samples. They are a representation of a sound wave. Okay? And there are sound waves that are high-pitched, and there are sound waves that are low-pitched. When you see a sound wave that is high-pitched, we say that it's a high frequency because the wave oscillates up and down very fast. Okay, high frequency because it's going to change rather fast. And when you hear something that is low-pitched, the wave moves a lot more slowly. Okay. So what we want to do is an EQ. The purpose of an EQ is that it will attenuate or boost certain frequencies. So what we want to do is we have this series of numbers that are coming in, and we want to manipulate their rate of change. If the numbers are changing very fast, it means that our wave is moving super fast and we are sampling that and the wave is moving fast. So we have numbers that change very fast. And we can make the numbers move more slowly if we want. The sonic effect of that, if we make the numbers move more slowly, is that it behaves like something called a low pass filter or high shelf, or there are different names for this, but the effect is that you will hear more of the lower frequencies, more of the bass sounds, and you will hear less of the high frequencies, the more high-pitched sounds. So what we're going to do at some point is to manipulate these numbers so that they move more slowly, or alternatively, if we want to boost the high frequencies and tame some of the bass, what we'll do is make the numbers move faster. Okay, so judging by the picture you found on Google, a whole moving average is a way to get a number that moves very fast, like a stock market. It seems to be used in economics. So it's a number that is moving very fast. How much is Apple worth right now? It's moving all the time. But you don't really care about how much Apple is worth at 3:15 p.m. You care about how, in some contexts, right? In some contexts, you care about how is that moving over time? How is it? Am I going to make money or lose money if I invest on that company? So you do this average, which will smooth out that weird curve with lots of ups and downs. It will smooth that out into the red curve. And you can see that the red curve is moving more slowly because it's smoothing out the valleys and the hills. So, in other words, this is a low-pass filter. If that weird thing was not some stock markets thing, but instead was audio, you would hear it as just a lower frequency, as a low-pass EQ.
That's cool.
So anything that you can do to manipulate the rate of change in numbers, you'll be able to apply that to EQ. And it's interesting because if you start reading about this, you see some explanations that are about stock market stuff, economics, algorithms that were developed by economists that can actually apply to audio and vice versa.
Cool.
Yeah. But in particular, the whole moving average is not something that I know by name. It may be something that we will implement because I have an idea of how I want to implement this EQ because it will be pedagogical. It will not necessarily be super useful at first, but it will be a cool way to show all these concepts at play. And I don't know if the whole average is the thing that we are going to implement, but we are going to implement something very simple to begin with. And then we'll get more complicated stuff later on. And boost.
I had a question about that. So you were saying, it's really interesting because I mean I've used EQs forever. I never really like gave thought to the underlying code. So you were saying, okay, like we slow down the rate of that the samples changing and we get like a low pass. So what happens when we boost? How do we, in terms of like what happens to our on a sample level? What happens when I like boost 20 dB, like 3 dB? How does that work like to the maths?
Yeah, so there are two questions here. The first is how do you boost a certain frequency by manipulating the rate of change of the numbers? And the other question is how do we make this relationship happen between like I want to boost 20 dB. How do I come up with a corresponding number that I will have to change by in my samples, right? So the second question, this relationship is, the answer to this is, it's complicated. I don't know much about this myself, but I'm trying to learn. So what I can do right now is find the right sources and copy and paste the ideas and implement them in JSFX. That's what I can do so far. But I don't fully understand the mathematics. And it is, in fact, like a PhD to really come up with these equations.
Yeah, absolutely.
It is something that is super hard, and it's super useful too, because if you come up with a good set of equations that has a bunch of nice properties, you can apply that to economics, to geophysics, to audio processing, to video processing, because video is just a bunch of numbers as well. So you can apply that in several areas, and it's super interesting, but I don't know much about that. That said, let's tackle question number one, which is how do I boost something? Well, suppose that you want to boost high frequencies, and the numbers are changing just slightly. The numbers are going from 0.1 to 0.2 to 0.1 to 0.2.
Oh, you multiply.
What we can do, not quite. If you multiply, you would get a signal that is louder. If you said something like 1.05, 1.5, 1.05, 1.5, but at the same rate, you would just get a louder signal with the same frequency. Right? You're just making the sound wave taller. In other words, the sound wave, the thing that we see on ReaFir, the peaks that we see in ReaFir, it is a plot of time on the x-axis and the positions of your speaker cone on the y-axis. So you can imagine that the speaker cone is right here and you're looking at it from the side, and your speaker cone is doing this, and it's moving air, and that's the sound wave that you hear. So these waves that Arya is showing is where is your speaker cone right now, and then it's moving back and forth following that pattern.
Very cool.
And so if you just manipulate these forms by multiplying by a value, you will just make the waves taller, which will make your speaker move more to the sides, pushing more air, and we hear that as louder. But if you want to change the frequency, you have to change the rate at which the thing is going up and down. So instead of saying 0.1, 0.3, you can say maybe, I guess it's easier if I explain the other way around. If you want to tame down the high frequencies, okay, I'll start with this. So if you want to do a low pass filter, you say 0.1, 0.2, 0.3, 0.2, 0.1, 0.2, 0.3. You see what I mean? What you're doing is you're making the speaker cone move more slowly, not making it move more or less. It's still going to move the same amount, but it's going to get there more slowly or more fast. And that's what we perceive as a difference in pitch.
Yeah,
cool mathematics, huh?
I love this stuff.
Yeah, and if you want to boost high frequencies, you would do just the opposite. So if your wave is moving like 0.1, 0.2, 0.3, 0.2, 0.1, 0.2, 0.3, you just skip some. And you say 0.1, 0.3, 0.1, 0.3. There you go. You just boosted the high frequencies.
Yeah, Bo says, so the Hall average adapts quicker to the energy of the signal. I'm thinking it might sound cool to test on audio material. It adapts quicker, wouldn't it? Oh, okay, it adapts. Okay.
I guess what this means is that the red wave on that picture you found on Google, the red wave follows the, I guess, the black wave, which was like the stock market. So the red wave follows the black wave more closely or more quickly. And we could test that on audio material. Yes, we could implement something like this. Probably not today, but we can do it. And Bob's NY says, I think it's very hard to understand how to slow/increase a wave without changing the frequency itself. I digress. Yeah, so we have to understand that these two things are separate. One thing is how high and low the wave goes. That is how much your speaker cone is moving, how much air is pushing to your ears, how loud you are going to perceive that. So that is just how tall the wave is, the intensity. Right. And that's what you measure in dB, by the way. That's what you measure in dB, how tall the waveform is. And then the rate of change is how slowly or how fast the thing is going up and down. That's the frequency. Okay, so those are a lot of terms. Have you heard of an effect called ReaFir? Yeah, so it is a bunch of things. ReaFir is a bunch of things, but one of the things that it is an EQ. And sometimes people use that to analyze a profile of noise, and then they apply that EQ to a signal and try to remove noise that way, right? So it's an EQ that allows you to do some lightweight noise reduction. I think that's the claim to fame for ReaFir. Yeah. So let's talk about how ReaFir does EQ and why we don't want to do it like that. Yeah. So the way that ReaFir works is it listens to the audio, it finds all the frequencies in the audio, it does some weird mathematics to find those frequencies, and then it does some weird mathematics to push down on some of these frequencies and push up some of the other frequencies. And then it reconstructs a waveform back to you. Okay, so there is this translation from waveform to essentially a spectral analyzer, essentially the thing that you see all the frequencies in when you play some audio through that. So it does that manipulation, and then it converts back from the spectral analyzer into a waveform. When I say things like spectral analyzer, does that make sense to you?
But maybe we should explain it in case somebody out there, doesn't.
Yeah, so can you do something for me? We could just play some audio, but I want to be more mathematical about this. So can you put on an effects chain? You put a tone generator, a white noise generator.
Let me just move some stuff around.
And make sure you mute the track, okay?
I always put tone generators and stuff on items, so that way they just never make a sound until I glue them. So tone goes first, white noise goes next. Does this actually do white noise? No. Where is my white noise generator? What? Yeah, white noise generator. Okay.
And then put whatever EQ you like that has a spectral analyzer, or you can put the spectral analyzer that comes with ReaFir.
I'll put the ReaFir one just so everybody has it. No, where is my trusty? Oh, spectrograph, do they call it, right? No.
No, I think it's Spectral Analyzer.
This one, right?
Yeah, Frequency Spectral Analyzer. There you go. Okay, so disable or bypass the white noise generator and enable the tone generator. And I want this to actually play, so I guess what you have to do is play the ReaFir timeline.
It's now sending to our frequency analyzer, but we're not seeing it. We're not hearing it.
But I hear
it
it
a little bit. I just turned down the slider to like -40. Do you want to hear it more, or?
Just to show what it looks like, and we can hear low frequencies versus high frequencies. Bring it down. It's kind of loud.
Is that good?
I think so. And move the tone. So in the tone generator effect, you can change the frequency, but keep the spectrum analyzer open while you do that. So double click on the spectrum analyzer. There you go.
Cool, and I go.
Yeah. Stop that. Okay, so we just saw a spectral analyzer. It is a different way of looking at sound. One way of looking at sound is what we just looked at before. It's the sound wave, literally. So it is a plot of time over where is your speaker cone. That's one way of seeing things. Some people call that peaks in ReaFir. Some people call that an oscillator. It's just a representation of where your speaker is over time. That's one way of seeing things. Another way of seeing things is with a spectral analyzer. What this is showing is on the x-axis, we have frequencies. Low frequencies on the left, high frequencies on the right. And on the y-axis, we have the intensity of that frequency. So in a signal like the one we were hearing, we could only hear some bass sounds and then some high-pitched sounds that sounded super annoying. And we could see the wave moving around on the spectral analyzer. Okay, so the way that ReaFir works is a very intuitive way to construct an EQ, because the way that ReaFir works is it takes a sample of audio in that representation that we were looking at, so a sound wave over time, your peaks, your oscillator. So it got that representation. It converted that representation using some very cool mathematics. It's something that you may have heard, a fast Fourier transform. That's what it does. So it does a Fourier transform to go from that representation into this representation with the graph, with the frequency spectrum analyzer. So it goes into that representation of the sound. And then it does some cool mathematics, but essentially what it's doing is, you can imagine that it's just looking at the curve and it is like multiplying by a value, let's say. If you multiply by a value between some parts, so let's say that you multiply by half when you are between 200 hertz and 2000 hertz. Okay, so what you're doing is just you're bringing that part down. It's going to be quieter. So you're attenuating those frequencies. Right? Okay. So that's what it does. And you could see literally just the wave being squashed down. In some EQs, you see that. You see the original wave and you see the new one that has been attenuated or boosted. And then ReaFir does the travel back, because the cool thing about a Fourier transform is that you can always invert it. So you can do an inverse Fourier transform, and you can go back into that representation with sound wave over time, which is good, because ultimately that's what we need to compute. We need to say to the speaker where it needs to go. That's our job. As audio effect programmers, we need to say to the speaker where it needs to go. And so that's how ReaFir works. And that's very natural, right? If we are writing an EQ, that's a very natural idea. Oh, there is some black box that is the Fourier transform, and it's super cool in that it gives us this translation between the two domains, between the domain of time, which is a sound wave over time, and the domain of frequencies, which is the spectral analyzer. Okay? Now, why is this a bad idea? And why don't we use ReaFir as our main EQ? Do you use ReaFir as your main
No,
EQ?
just because I use RX, but I'm sure it's useful. I just never dove into it.
Yeah, ReaFir is good for things like noise reduction, because you want to analyze the noise profile. You want to give it some noise, and then it will learn that the noise has
Right.
this shape. So my EQ will not be like boost frequencies between 200 and 500. No, it will be like super tailored to your noise. That's cool when you want to do something like that. But in general, when you're using an EQ, you don't want to use
Right.
ReaFir. Reasons. It introduces a bit of delay, and it introduces some ghosts. Ghosts, what is that about? You will be able to hear some backwards echoes if you go really far with ReaFir.
Yeah.
Backwards echoes? What is that about? Have you heard backwards
Yeah,
echoes
I've
before?
definitely heard when you like overuse any kind of noise reduction plugin, there's that like weird echoing happening. I don't understand why it happens. Okay.
Now you will, because these plugins that you're using to reduce noise are using this technique that we are describing right now. They are doing some analysis of the noise profile. They're going to hear, oh, there is a lot of noise in this frequency over here. So, and it's not like a frequency between 200 and 500. No, it is between 200 and 200.1. There is a lot of noise. So I will attenuate that. It's super precise. It is like a very focused EQ, and it can find all the points that it needs to attenuate, which is great. The problem is these backwards echoes, they are not, when you record something, put an echo and reverse the audio. No, that's not what this is. That's a cool effect. It's something that we do sometimes, but it's not what this is. When you do this black box transformation between the time domain, the waveforms, and the frequency domain, what we see in the spectral analyzer, when you do this translation, we cannot do this as the samples are coming in one at a time. It's just the nature of the fast Fourier transform and the Fourier transform. It's just the nature of the game. It's how the universe works. The way that we know how to do this translation. We cannot do it one sample at a time. Which I guess makes sense, because if I ask you, what is the frequency of the sample 0.1?
Right. Yeah. It only samples 0 and 1
I don't
out
know.
of it, right?
Yeah, you need to know that it is 0.1, 0.3, 0.1, 0.3, and then you're able to tell, oh, okay, it's moving at this rate. This is the
Right.
frequency. Okay, so this fast Fourier transform and its inverse is not free. You have to collect some samples before you can do it. And similarly on the way back, you need to collect some samples before you can go back. So that's why introduces this ReaFir introduces a bit of delay, because it needs to collect some samples before it can do any work. And the backwards echoes are even more interesting, because you collect some samples, and then you do the fast Fourier transform, you go to the frequency domain, you get your spectral analyzer. Then you do whatever manipulation you want to do, and then you start converting back. On this forward conversion, we lost some information about the time of the frequency. So about the timing of the different frequencies. So maybe let's say that we have a window, and that's another thing. You need this window, right? You need to collect some samples. So there is this window. So you have this window, and suppose that there is some high-pitched sounds in the beginning and low-pitched sounds at the end. Now you go to the frequency domain, you see a bump in the beginning and a bump at the end, because there are some low frequencies and some high frequencies. But what you lost is information about the sequence, the timing. You don't know which happened first. You know that there is some high frequencies and low frequencies, but was it low-high or high-low, both at the same time? Impossible to tell. We lost information about the timing of the samples when we did the fast Fourier transform. And then when you come back, yes, it is this inverse fast Fourier transform is kind of magical, because it, given a spectrograph or a spectral analyzer, it will give you back the waveform, but it doesn't know if it should order low and high or high and low or both at the same time. It lost some information there. So if you have a sample that, if you have a window that is maybe just silence and some high frequencies. When you do this journey, you may come back with some high frequency and then some silence and then some high frequency and some silence. It's crazy, right? It's difficult to tell what will happen. So you lost some information there about the timing within a window. And what sonically we hear that as a backwards echo. We hear the echo of the sound before we hear the sound itself, because we lost this ordering information within the fast Fourier transform window.
Very cool.
And that is why it's useful to use ReaFir for some very surgical removal of noise, which is usually very subtle. You don't do a lot of boosts and cuts with noise reduction. The more you do, the more artifacts you will introduce, and the more like a robot you will sound. So you want to do everything very, very slightly. So ReaFir is not your guy if you want to EQ some guitar and you want to remove the low end. That's not your guy, because you're going to lose information about the timing, and you will hear some echoes of the guitar before you hear the guitar itself. And it's not like a long slapback echo at the border of a canyon. It's going to be just a weird sound. Sometimes you may want that for aesthetics reasons, but if you want your EQ to be clean, you don't want to do
I was gonna say, when like once I had the sound design for like this weird speaking robot that was kind of broken, so I used something similar to ReaFir, which just introduces so much artifacts that it sounds like now you got like a malfunctioning kind of robot. So you can use it as an effect for sure.
Yeah, but you don't want that to be your main go-to EQ. But why do I mention ReaFir just to say that it's not useful? Well, because it is the most intuitive approach. The most intuitive approach is, instead of trying to work with samples, let's collect the samples, put them on a fast Fourier transform box. We'll get a spectral analyzer, we work on the frequencies however we want, and we go back. We have a lot of control. If you want to multiply by maybe 6 dB, you just multiply by 6 dB and you will boost that frequency by 6 dB and it will be great. So it's very natural to think in these terms. And as a beginner, I was thinking in these terms as well. If I want to do an EQ, I will have to do this. And it's not that hard to do in JSFX. In fact, one of the few things that comes in the toolbox with JSFX is a fast Fourier transform and an inverse fast Fourier transform. So we don't have to code that by hand. You can just call a function. We give it a bunch of samples. It gives us essentially the spectrum analyzer output that we see on the screen, but with numbers. Okay, so why not do it this way? Because of the artifacts. We don't want to do an EQ this way because of the artifacts, unless you're doing something like ReaFir, which is more niche. But for a general EQ, we don't want to do that. So what do we do instead? Well, we do some magic. We look at the samples coming in, and we apply some idea to change its rate of change. So we will make it change more slowly. For instance, we talked about this, how you can make it change more slowly, go from 0.1, 0.2, 0.3, instead of jumping directly from 0.1 to 0.3. So we are going to do some cool mathematics to change the rate of the wave coming in. But we are going to do that at the time, in the time domain. We are going to do that as the samples are coming in. Our EQ will have no delay whatsoever, and it will not have the weird backwards echoes artifacts. But then the question becomes, okay, but how can I manipulate the frequencies with any precision? What do I do with the samples? Right? How do I compute the rate of change? And if I want to boost at 2000 Hertz, how do I know what to do with the samples? That's when the very advanced mathematics comes in. There are some fixed formulas that you can manipulate and that will take as inputs the samples, and that will spit out new samples, and that will have a certain effect on the frequencies, on the rate of change. And I guess what Bo was mentioning before, the whole moving
Right.
average is just one way to do this, to manipulate the rate of change.
Very interesting.
Yep. Yep. So that was a lot of me talking and no programming, because I was giving you all a long-winded introduction on the world of EQs and how they work and why you want to do EQ on the time domain as opposed to doing it on the frequency domain. And all EQs you use, from FabFilter to Ableton's EQ, everything in ReaFir, ReEQ as well, as far as I can tell, they are all doing it in the way that I explained, in the time domain.
So, like, I guess this is when you talk about like a linear phase EQ. So when you do EQing in the time domain, then you are affecting the phase. So this thing is always like a trade-off, right? Like, if you go in the frequency domain, you are making time mistakes, like that pre-ringing or those echoes. And then if you do it in the frequency domain, then you are causing and if you do it in the time domain, then you're causing like another type of issue, right? It's never like, oh, this EQ will just do everything perfectly. So when they say linear phase, is that working similar to like the FFT in ReaFir?
There are some things you can do in the time domain without having to go to the frequency domain, without having to apply any fast Fourier transforms. You can do some manipulations that will affect the phase, and you have control over that. So it's all in those mathematical formulas.
Cool. I'm just going to grab some water real quick because it's an incredibly hot day. Bops NY, are you based in NY? Because how hot is it there? I'll be right back.
Now it's just me and you all. Bo, you seem to know a lot more than I do about EQs. Do you have an idea of how we should implement this? I have an idea, but I wanted to know if you had another idea. I mean, do you know how to implement the Hall moving average you mentioned?
Okay, I'm sorry. Oh, you're in Florida. Yeah, it's
even worse, I guess.
Yeah. Global warming. Cheers.
Yeah.
Okay, so this is interesting because I remember when I was learning Max MSP, somebody asked our teacher, like when we kind of finished Max and we were starting on MSP, somebody was like, well, let's start by making an EQ. Like, that should be the easiest. And the teacher was like, no, that's the hardest. Like, you can make delays, you can make all sorts of like super weird, like phasey effects and stuff quite easily in Max MSP. But then when you get to EQ, it's like, wow, this is getting like out of that object based, and now you gotta like get into the math of things. So now I'm also kind of realizing that like from the user kind of point of view, from like the audio person, you're like, EQ, that's just super basic. But from the coding, it could be the reverse, because if it was a delay, it's like, well, copy my audio, play it later, you know.
Yeah. Well, the cool thing about an EQ is that it at the same time super complicated and interesting, at the same time super easy. It is the easiest because the mathematics behind it is interesting, and we have been discussing this for 40 minutes now, how it works and why you want to do it this way and not that way. But when we end up coding the thing, it will be like 5 lines of code, I promise. And it will not be difficult lines to write. It's just difficult to understand what they're doing, but the lines are easy to write.
Cool.
Okay, so do you want to jump in the code and actually
Sure.
start writing something? Okay, so we are going to do a very, very, very basic EQ to begin with, okay? But it will, we will be able to manipulate samples. We will learn the basics of how we can make things sound different in a JSFX. So let's start by removing all the sliders. Our EQ is so simple that it doesn't have any controls for you to play with.
Bye.
So remove all the sliders. And these next lines, we haven't looked at those. They are the pins. So your effect can have different inputs and outputs. Maybe your effect will be stereo, maybe it will be quadraphonic, maybe it will take however many inputs you have. And you can see all those pins in the in and outs. When you see the plugin interface there, it's 2 in, 2 out. And that's how you connect the cables between the plugins. And you can be explicit and you can give names to these pins. You can see here on the plugin pin connector that the pins have names, and you can change their names. Sometimes you want them to be the inputs. Sometimes you want to do something like another audio input that manipulates how the effect works, but you don't hear it. So it's not really fair to call it a left and right output or input. It's something like a side chain. There is this thing called a side chain for things like side chain compression. And the side chain is the audio that will be analyzed to manipulate the gain, because that's what a compressor does. It manipulates the gain, but it doesn't, you don't hear the side chain. You don't hear that audio signal. So you may want to name these things accordingly. But in our case, our effect is so simple that it has no side chains. It has no need to name pins. So you can remove all those lines as well. And then we see some blocks. In JSFX, we have several blocks of code, and they run at different times. You can go ahead and remove all those 4 lines. In pin, out pin, you can remove these 4 lines. We don't need to name our pins. So there are these blocks. They are represented with @ and then a name. If you want to learn about all of them, they are documented in the ReaFir website, but we can talk about the ones we are going to need. So remove all the code between, you know what? Leave the code there. I'm going to briefly explain the blocks that we have there and why we're probably not going to need them. So the @init block runs when you load the plugin into an effects track, and it runs when you hit play. So when you start processing audio, it runs that block of code, and that's where you do some sort of initialization. I don't think you can put a comment there, and if you can, I don't think you can put a comment there. But if you could, the comment in JSFX is with // not with --.
Okay, cool.
Yeah.
Okay.
Yeah. So
I'll just watch this later again and take notes. So cool. Keep going. Sorry.
Okay, so the init block will run when you start, and that's where you do some initial computation. Like I said, there will be mathematical formulas later, and some parts of the formula you can compute when you start because they don't change. So you always have to think about performance when you're writing JSFX, because real-time computation of audio is it's intensive. So if you can do something and reuse it, do that. Okay, so the init block, I don't think we'll need, so you can remove that block. Then there is the slider block. The slider block runs anytime you change the value of a slider, either because you're literally sliding or because you wrote some automation into a track. And the cool thing about using sliders is that you can put automation, you can put them on the track control panel, you can do anything you would do with any control on an effect, you can do with these sliders. It integrates very well with the rest of ReaFir. And then again, there are some things that depends on your sliders. So maybe if you say in your key that you want to boost by 20 dB, you can do some computation when you change the slider, but then you can reuse that value later on. But we don't need that block on our effect. So you can remove the slider as well. Next, we have this block called block. What the block does is it runs on every block of samples. And this size of the block is, I think, related to, but not exactly the same as your buffer size. So in ReaFir, you can increase or decrease the buffer size. So if you want things in as much low latency as you can, you decrease the block size. And if you want to have more audio effects and more tracks in your project and your computer is not fast enough, you increase the block size so the computer has more leeway. There is this buffer that it can work with. And I believe that the block is related to that block size. And then that block of code will be called when ReaFir has collected, in your case, 1024 samples, it will call the block.
Cool.
And sometimes you can do some computation in blocks. So I guess maybe a fast Fourier transform is something that you could do in a block like that, because you have to collect some samples. But we don't need to work with the block. So you can remove the block.
I'll just close this. Bo has an interesting comment. Yeah, like if I want like a random EQ, like just using a Lua script to control a regular EQ, which I guess is also cool if you want to like learn an emulation EQ or something like that. So you can have a Lua script like either turn up this gain or this gain or this gain. That's a cool idea. Yeah.
And it will probably be easier to implement in Lua. Okay, so now we have this last block. And this one I think we will need because it is the last one. So what this block does is it runs on every sample. And that's what we are going to do. We are going to run our effect in every sample. And so this is a block of code. It's going to run on every sample. It's a block of code that is going to run 48,000 times per second, or whatever your rate is, your sample rate. And in this block, we will have an opportunity to manipulate the samples as they come in. Okay, so what the boilerplate, ReaFir put some boilerplate code for us in the text editor when we created the effect, right? And what this boilerplate did was a gain plugin. So let's play around with this gain plugin, which is probably the simplest effect you can write. And I kind of already mentioned the way that it works. It works by taking a waveform and squishing it to make it quieter, or expanding it to make it louder. So let's play around with that. So go back to the effects chain, save this, and make sure that you save so we don't lose this. And it will be okay. It will blow up in several ways, but it's okay. So now in that other track, we had a chain of effects. We had a tone generator, white noise, and so forth. Can you go back there?
Where's the third one? Okay, yeah.
Yeah, so leave the tone generator, but put our plugin between the white noise and the frequency spectral analyzer.
What do we call it? Random EQ. Okay. Oh, it went to the bottom. Get up here. Okay. We don't need to see the spectrum analyzer now?
We don't need the spectrum analyzer, but I will ask you to put another effect on the track, which is an oscilloscope. An oscilloscope. And while you are doing that, I'm going to explain what the oscilloscope is. The oscilloscope allows us to see in real time the waveform. So when you record something in ReaFir and you zoom in very, very close to the waveform, you start to see the wave, which is the thing I mentioned before. It's where your speaker cone is over time. That's what that graph is. And I'm talking about the oscilloscope that comes with.
Sorry, I have your video on top of my screen, so I actually don't see my my screen.
Two below.
Oh, oscilloscope meter. Okay, there we are. Okay.
There you go. That one. Yeah. So Now, you can turn off the frequency spectrum analyzer, but leave it on. It doesn't affect the audio anyway. But put our effect between the white noise and the rest, because we'll need this later. So what are we doing here? We are creating some noise, either white noise or a tone. Then we have our effect, the one we are developing, and then we have some analysis tools, like a spectral analyzer and oscilloscope, so we can see what's going on. We can also hear what's going on, but it's nice to see sometimes. So now enable the tone generator and disable the white noise, and make a sound.
It should be making a sound. I'm wondering, is it because...
Oh, our effect is in the middle and it's messing things up. Bypass our effect.
I'll turn this down again. Yeah, there it is. There's our tone.
Yeah, now in that window, this is also a JSFX, but it's one of the fancy ones that has a graphical user interface. And we can see the shape of the wave in real time, which is super cool. Now, can you leave this window on the side? And let's play around with the tone generator. So leave this window open on the side and go back to the tone generator. And leave the frequency untouched, but you can change the loudness of this by changing the wet mix. And you can see that the wave gets taller and it gets shorter, but it doesn't change the rate. It is still going up and down at the same rate. You know what? There is something in the oscilloscope that comes with ReaFir, which is super nice. It's called retrigger. So this first, no, retrigger. So click on retrigger. Okay, so what it's doing now is it is just updating the screen differently. It's still capturing every sample, but it's only updating the screen when it sees a zero crossing. So now we can see that the length of the wave remains the same when you change the loudness. And if you want, you can put the audio through so we can hear the changing loudness, but don't make it too loud. But you can also just trust me, it will be louder as you make the wave taller, but it doesn't change the rate of the wave. It still occupies the same size on the screen, left to right. Like
this. I love the scale that's created when you randomly sweep frequencies. It's always weird. Sorry, side note. Yeah, cool. I'll turn this back. We'll see the signal, so we're looking at the signal more than hearing the tone, because the tone kills me.
Yeah, and we will see some things that will make sense, and then we'll be able to hear some things that will make sense too. But it's always good to see what's going on, because we are manipulating numbers. Each sample is a number on this graph, and we are changing those numbers, and we'll be able to see what we are doing. So now let's go to leave the oscilloscope open on a window and go to our effect and go to the source code for our effect.
Source code, here we go. Okay.
Okay, so now you can remove this last line. It doesn't do anything helpful.
Boop.
Yeah. And now let's understand the two lines that we have there. By the way, change the last gain to the number 1 in both lines.
1. Okay.
Thank you. So what we have here, we have a sample block. It's going to be code that runs on every sample. And in this block, we have access to many variables that ReaFir gives us. So, for instance, when we were writing ReaFir scripts, there was this all these ReaFir functions with the ReaFir API that was just available to us. In JSFX, we have a bunch of variables that are just available to us. We can just use them. So one of these variables is SPL and then a number. And it goes from SPL0 to SPL64, 63 actually. These are samples. SPL stands for sample. So we are getting samples from 0 to 63. They are different channels. So we have a stereo signal right now. So we have SPL0 and SPL1. If we had quadrophonic signal, we would go from SPL0 to 3. If we had some track with 64 channels, which is the maximum in ReaFir, we would have from SPL0 to 64. And on the right-hand side, there is the system's variables panel, and we can see all the samples in real time. So maybe you have to save this, I'm not sure, but make sure that it's...
yeah, so 0 to 63 though, I
Make
think
sure...
you misspoke, but yeah. So 0 is the 1.
Yeah, it goes from 0 to 63, and you have to enable the effect.
Oh,
it's bypassed right now.
enable boop.
And then you see the numbers changing on the right. These numbers are the samples in real time. They are the numbers that are being plotted on the oscilloscope. You can see that the numbers are between like minus 0.15 and 0.15. And it goes to minus 1 to 1. So the loudest sound you can make in ReaFir goes from minus 1 to 1. And if you go above if you go above 1 or below minus 1,
right,
you clip.
Like this. We went to 1.2 just now.
Yep.
Yeah, 1.06, 1.7. Jesus.
Yep.
All right.
Yeah, it's good that Aria muted this track because that would be absurdly loud. So we are working with numbers between minus 1 and 1. That is the magic. All we ever have to do when writing audio effects is to manipulate numbers between minus 1 and 1. How hard can this be?
It's so hard because Max MSP is the same way, and it's a lot. It's many decimals too.
Yeah, so now make the waveform a little bit bigger so we can actually see the waveform. And now let's see what these lines are doing. In our effect, we have SPL0 and SPL1, and they are both, there is this star equals operator and then 1. The star means multiplication, and star equals means multiply the sample by this number. So we can rewrite this line, in fact, as SPL0 equals SPL0 star 1. It's the same thing. It's just another way of writing it. So this is multiplying a sample by 1. And as you may know, multiplying by 1 doesn't change a number at all, right? But if you multiply by, for instance, half, that will make numbers that are like 0.1 will become 0.5.
0.05, right?
0.05. So numbers like minus 1 and 1 will become minus 0.5 and 0.5. So it will become quieter. Save, and we'll see that on the
should I do
the
it
waveform.
for both channels?
And then if you do it on one channel, we'll hear a quieter sound on the left and a louder sound on the right.
Whoop, there it is.
And now on the oscilloscope, you see both channels. They are rendered with different colors.
I got a side question then. So I guess if we multiply by negative numbers, then that's like inverting polarity, right?
Yes, if you want to invert the polarity, you just multiply by minus 1. Yeah. And let's play around with the mathematics here. So how about we write it like this? First of all, forget about sample 1. Let's just work with sample 0. Otherwise, we'll have to copy and paste a lot. So let's just work with sample 0. And write it as SPL0 equals something. And then SPL0.
Oh, SPL0 times...
Yeah, so there are plenty of ideas. Now, this is the explosion moment. What if you want to invert left and right? You assign SPL1 to SPL0 and vice versa. What if you want to make one side louder than the other? You multiply one of the sides by one number and the other side by another number. What if you want to invert the phase? Multiply by a negative number. What if you want to do what is called a DC offset, a direct current offset, which is just making the wave is usually between minus 1 and 1. If we put it up between between 1 and 2, for instance, that's something called a DC offset. What do you do? Just add 1, for instance, to the sample. Go ahead and do that and save.
Let's add 0.5. Whoa, cool.
There you go, a DC offset. It goes to the top. And there is still the left signal that we are, the right-hand signal, the SPO1 that we are not manipulating. So we see that in a different color. which is good for reference. Now we can tell what we are making to the wave. And what happens if you add SPL 0 and 1 together? Then you are making a stereo track and you are mixing it down to mono. You are combining the waves. Right? So all these utility effects, they boil down to simple arithmetic manipulations of the samples. Isn't this cool? I find this fascinating.
Literally, yeah, having the best time.
So here is another cool trick. What if our sample is a random number? Then we will not have a shape that looks like this. Oh, by the way, what happens if we just say that the sample is the number
just
0?
Silence, right?
It's just silence. So you can replace all that with 0, and then we will see only the right wave, only SPL 1. That's what we are seeing right now. We no longer see the green. Okay, cool stuff. What if we make it 1?
It's just full 0,
it's just the number 1.
Like sitting at 0 all the time?
Yeah, it is not sitting at 0, it's sitting at 1. So what it just did is it pushed your speaker cone and it put it there.
I meant 0 on the,
so it's not making any
full
sound.
Scale, basically.
Yeah, right. Yeah, but it's not making any sound. Yeah, it's 0 on the dB scale. It's pushing the speaker cone to its maximum in one direction, but it's not moving it around, so it's not really loud. This is completely safe for us to hear. If you look at the meter, it may show that the thing is clipping. I don't know if it shows, but it may show that the thing is clipping.
Let me get but
it's not
meter too. Where is a meter? Okay.
I'm not sure it's going to show the clipping. It would show the clipping on.
I'll just do this. I'll make a send, and okay.
You don't need to do all that. Just go to our effect. Show the interface for our effect.
Interface for our effect.
So currently you have the code, but show the interface
for it.
first.
I put it somewhere, but it's under something.
Just click on random EQ on the effects list. There it is. So there are these nice meters on the left and on the right. The left is the input and the right is the output, and we can see that we are clipping on the left, but that's a lie. We are not making any sound on the left. The meter is coded very naively. It doesn't look at the pressure of the sound wave. It doesn't look at these things called RMS or loudness. No, it just looks at the peak. If the thing is at 1, it's peaking at 1. It must be clipping. It's not. It's not making any sound. So, but I was saying, what happens if you add SPL 0 and 1? You make a mono signal. And was I in the middle of something else? Am I missing something?
SPL 0 and 1. Oh, I had a question. Maybe you weren't talking about this. In essence, if I want just everything to apply to SPL 0 and SPL 1, if I like make a I hate this font because the L and the 1 look exactly the same. Like if I create a local variable here and then go SPL 0 and SPL 1 equal to that, then we change that variable, it would just apply everything to both signals, right? So it won't be mono, but it would be,
correct.
It would do the same operation to both sides, basically. Cool.
Yes. And one quick syntactical trick we can play is that in JS effects in EEL2, essentially the language we are writing in, it borrows many ideas from C, and you can do this in C and you can do this in AEL2 as well. So you can say SPL0 equals SPL1 equals and then something, and then what you're doing is you are computing the thing on the right and then you are assigning it to everything you see on the left. So this way we are assigning to both SPL 0 and 1 at once with a single line, which is useful for mono effects. And what do people usually do when they are writing code for this? Usually they hard code things to be stereo, and they copy and paste the code for channel 0 and 1, which I find super annoying. I understand that it's the fastest, but it's super annoying. First, because I may want to have my effect be multi-channel, and second, because there is Ctrl+C, Ctrl+V all over the code, which I find terrible. So there is a way for you to do this, which is good for mono signals, but if you have stereo signals and you want to keep them stereo and different, you can just write a loop and do the same thing for all the channels, not just two, but any number of channels. We'll not do that right now. We'll not do that right now because we want to finish RAQ, but it's something that you can do. And as I was saying before, yeah, what if the sample is random? So we can just completely ignore the audio coming in, forget. I'm not doing anything to the audio coming in, so there is a sine wave coming in, but forget that. I'll just produce whatever value, like we did. We did produce the number 0, or produce the number 1 before. So you can do that. You can completely ignore the inputs if you want. What if we just make this a random value? And at every sample, we pick a different random value. The way you do that is by using rand. And I forget the specific syntax, but I think it's just rand and then parentheses. And that will gives us open and close parentheses.
Oh, it will just give us a random
value. Will give.
There you go.
Yeah, and it seems to give us a random value between 0 and 1. But we want something between -1 and 1. So what you can do is just subtract by 1 and multiply by 2. So the other way around. Multiply by 2 and subtract 1.
So I can go like this.
So when you multiply by 2, you make it go from 0 to 2. And then subtract 1, and you will offset it down.
Boom.
Okay, so what do we have there? We have a bunch of random numbers. You can zoom into the oscilloscope, and you'll see that the wave is all over the place. Can you zoom in?
You zoom in?
You click and drag up. Oh, that seems to zoom into the thing horizontally. No? Can you? Yeah, maybe that.
Length just doesn't do anything. Yeah, okay, because this changes the range. The length is just... Oh, yeah, okay. So if I go like... I'm now at a length of 75 hertz. And now is see.
Yeah, so now we can see each sample. Each one of these dots, or I guess lines, they are rectangles. Each one of these is a sample. And you can see all the samples coming in. They are random numbers. They are all over the place. Do you know what that sounds like? That sounds like white noise. And that is going to be a great example of how we can work with an EQ. So go now to the frequency spectrum analyzer, and we'll see what our effect is producing on the frequency domain.
Sorry, Pop. Something is going awfully weird. Okay, yeah.
So now we see just a flat shape. Before, when we were working with sine waves, we saw the frequency of the sine wave as a spike. But now we see just a flat shape, and that is white noise. It has equal amounts of energy in all frequencies. It sounds like shh. It sounds like rain or a cymbal. Can you increase the volume? We should be able to hear that, but don't increase too much because we are producing the loudest white noise we can.
Somehow we're not getting... Oh, something is going on.
Oh, maybe it's muting the track to prevent loud noises.
So why don't I just take this... Why don't I times it by 1.5 or 1.2 or something?
Yeah, that will make the whole spectral analyzer go down, but it will still be a flat shape. And the oscilloscope will still be all over the place, but it will not go to the boundaries. So go ahead and save that.
Lamps. Why don't I just go divide by like -1.1?
That will just offset
things. Okay. So why aren't we getting... Because if we were getting it automatically removed, we would get... Oh, that's because I'm dumb, and I'm just...
Did you save the effect? Are
I
you sure
saved the
you
effect.
saved
I
the
was
effect?
moving the wrong fader. That's because I'm dumb. This is the... yeah.
Yeah. Sounds like
Yeah.
rain. That's white noise. And it's white noise that we created. Isn't that rewarding?
So cool, yeah. It sounds like somebody cooking bacon
Yes.
in the rain while there's a fire at the beach.
Yeah. So if you want to learn more about why a random number creates white noise, you can watch my video on white noise and explain why that is. But in summary, it is because it is creating all kinds of frequencies. It is creating all kinds of wavelengths. When you get two random numbers that are close together, that is like at least a little bit of a wave that is moving slowly. So it's slow. And then if you have two random numbers that happen to be far apart, they are moving very fast. So the rate of change is fast and it sounds high-pitched, but it's only a section. And it's putting together sections where the random numbers are close together and sections where they are far apart. So you hear all these frequencies. That's in summary what the random noise is doing. And what we want is to filter out some of these frequencies. An EQ does that. It will filter out some of the frequencies. On the spectrum analyzer, the frequency analyzer we are looking at, it will have a shape that is not just a rectangle. It will either be sloped like this or it will have a different shape. And in the oscilloscope, we will not be able to tell much what is happening. We will just be able to tell that it's not so crazy and all over the place. It will be moving in a more predictable pattern, but not by much. So we are going to work in this setup where we have some white noise, our EQ, and then the frequency and spectrum, and the frequency and oscilloscope, the spectrum analyzer and the oscilloscope. So now you can turn off the tone generator and turn on the white noise generator, which is basically just the JSFX implementation of what we just did. So there you go. We have white noise again. And now we can manipulate this white noise. You can enable our effect, and we are going to write our EQ. So let's start with the simplest EQ in the world. The simplest EQ in the world will just do a low pass, high cut filter. So the shape of the slope will be high on the low end and low on the high end. So it will look like you are sliding down.
Show this on a ReaEQ for people. It will look like... Oh my god, I'm doing so many things wrong. What the hell did I do? Alright, it will look like this. No, it'll look like this. Yeah.
Yep. That's what it's going to look like. And we'll do one of those. The low pass filter is the easiest the easiest filter for us to build. An EQ is just a series of filters working together. So we are going to start with the low pass. Then we can do a high pass. Then we can do a band pass. Then we can do and so forth. Okay. So let's start with the low pass. We have frequency all over the place, and we want to remove the high frequency. We want, if things are moving too fast, we are going to say, oh, slow down, move more slowly. And in effect, that is similar to what we saw in that image in Google, the thing that was like the stock market moving super fast, and we are going to slow it down.
Would that be by removing decimals?
That's an interesting idea. So if you remove decimals, that will be bit reduction. And there is a video, in fact, that's the first video I have in my channel in which I cover JSFX and I show you how to work with this text editor and everything. And I do a bit crusher. You're just losing information on the samples, but the samples are still going to change at the same rate. So what we want to do is to say, okay, if the rate is, let's say, it's going from 0.1 to 0.3 to 0.1 to 0.3 to 0.1, 0.3, what we want to do is 0.1, 0.2, 0.3, 0.2, 0.1, 0.2, 0.3, 0.2, 0.1.
Yeah.
See what I mean? So that will have the effect of a low-pass filter. Things are moving more slowly. Okay, how do we do that? The idea is super simple and interesting. The way that we do that is we are going to look at our sample, the sample that just came in. We're going to look at the previous sample, that one that was right before the current one, and we are going to average them. So Bo was talking about this whole moving average. So what we are building is something that is called a moving average as well. What we are averaging is the two most recent samples. And there is a fancy mathematical name for this operation. It is called, I think it's an infinite impulse response filter. There are all sorts of crazy language that people use when talking about this, but all you have to learn is that it's an average. Do you know how to compute an average? You know how to do an EQ. So how do we get a hold of the previous sample? That's a good question. How do we get a hold of the previous sample? Well, in the sample block, it's already too late because the sample is already over. We are running at the current sample, so we don't know the previous sample. But here is a trick. Every variable you define in the sample block or whatever block, okay? So every variable you define will continue to have its value on the next time the sample block is executed. So the next time we go around, the variable will have the same value. So, for instance, say that we have on the sample block, go to the sample block, and you can create a variable just by using it. You don't have to define anything. You don't have to use the keyword local like we had to do in Lua, none of that. So just create a variable named, what is a good name for a variable?
Sample.
What is a name that you like? Okay, previous sample.
Previous sample equals. Oh,
equals.
Of course, spell it right.
So yeah, previous sample is equal to maybe the number 0. Say it's the number 0. So, and then semicolon. So in Lua, we didn't have to put semicolons, but in EEL, we always have to terminate our lines of code with semicolons. The sample line is not a line of code. It's just declaring a block. The desk line in the beginning is not a line of code. It's just a description, but the code needs to end in semicolons. And save that. And then scroll up on the right pane, and you'll see the previous sample equals to 0.
Yeah.
Here is our variable. But I said that the variable remains with the same value the next time we go around. So here is a cool trick. We can say previous sample equals to previous sample plus 1. Or equivalently, plus equals 1, if you want to be concise.
Plus equals 1. Okay, I see. Plus equals 1. Like this, and line break.
Semicolon. And then save and pay attention to the column on the right, the value column. Cool. It keeps increasing because it's looking at the previous value and adding up. In fact, this number is increasing at your sample rate. After 1 second, the number is 48,000. At 2 seconds, 2 times that, and so forth. Cool stuff, huh? So you can count your samples. But that's not what we want to do. What we want is to have access to the previous sample. Well, what if in one run of the loop, we collect the previous sample, and on the next one, we can use it? Cool, huh? So all you have to do is move this line called previous sample to the next line. So as the last thing we do in our effect, we are going to collect what is the previous sample. So move the previous sample line to be the last line.
Whoops, missed the semicolon. Okay.
And then don't say plus equals because we are not adding things together. We'll just say SPL0.
Equals SPL0? Cool.
Yeah. And I messed it up. It should be the first. Hang on, let me think.
Is it expecting a string and it's...
No, that's right. I'm just thinking about the ordering of the things because we are going to change sample 0 and we are going to collect sample 0 as well. So the we are manipulating the sample before we collect it, which doesn't make sense. But before, we were collecting the sample before we actually used it. So that doesn't make sense either. In any case, I think I know where I'm going. So all we have to do now is delete the line that reads SPL0 equals SPL1, blah, blah, blah. Just delete that because it was confusing me. So now we have before, hang on. Yeah, before this line, before the previous sample line. So before this line, when you use the previous sample variable, it has the value of SPL0 from the previous loop. Does that make sense? Okay, so now we have access to the current sample, it's called SPL0, and we have access to the previous sample. So we want to average these two.
Divide them by 2?
Yeah, exactly.
And
so go ahead and do that.
Before.
Right, previous sample. Yes, let's do that before. So previous sample plus SPL0 divided by 2.
0 divided by 2. We don't need to abide by any of these math rules of parentheses I was about to ask. We need to abide by those?
Yeah. Yeah, if you don't put the parentheses, then you are dividing SPL0 by 2, but we want to divide the whole addition. So now we have what we want to be the current sample, right? It's the sample that has that is the average. So let's create a variable. You may want to call this the average, or you may want to call it the current sample. Call it whatever you want.
Average, average equals.
And then put the semicolon at the end of the line. And then as the last line, you can say that your SPL0 equals SPL1 equals average.
SPL0, whoa. I'm sorry for all my typing mistakes. Equals average. So I have a question. So normally, like for example in Lua, we have to define something like we're defining this previous sample in the next line using it in the previous line. In EEL, this is okay?
It is crazy. So any variable you come up with will exist as soon as you start using it. And it will have 0 as its value by default. So that's another interesting thing about variables in EEL too. Because they are meant to manipulate audio, and audio is just numbers between -1 and 1, all variables in EEL2 are numbers. They're all numbers. And if you try to use a variable that doesn't exist, its value is 0. And it starts to exist as soon as you use it. In fact, you had a typo there. You had average L. You fixed it. But before you fixed it, it was going to be 0. So if you saved that, it would just mute everything. You know what? Introduce the typo again.
Cool.
Put the typo in there. Save.
And save it. And it's gone.
And save. And see on the right, average L equals 0. And you never said, but it is 0. Yeah, and it is cool for us to define a variable after we use it because this thing is a loop. It is always running. So initially it will be 0, but on the next time we go around, it will be SPL0 from one iteration ago. So that's fine. And now fix the typo.
And we're back to getting something.
And we see a slope at the end. The slope is subtle, but it's there. Yeah. You can see that we are losing some of the high end.
If we A-B it, you will see it.
Yep.
Cool.
There you go. Now, you're going to say, oh, this is underwhelming. We don't have any controls over how much we are attenuating and what we are attenuating. But never mind that. We just did a low-pass filter. We did a sort of an EQ. Isn't it amazing? And we did it from first principles. What we are doing is just, we are making the rate of change in the variables decrease. We are decreasing the rate of change because we are taking the average. So if it goes 0, 1, 0, 3, 0, 1, 0, 3, it now goes 0, 1, 0.0203 because 0.2 is the average between 0.1 and 0.3, right? So we are just taking the average. So we are smoothing out this crazy thing, and that's how you make a simple low pass filter.
I'm just
Now,
paying attention to comments. Bob's not sure what you mean by delete random. Which?
probably we had some random
Okay,
somewhere in the code.
Cool. Sorry, we caught on late.
I think we deleted it already. Yeah. And Bo was saying that we could use an exponential averaging. So yeah, that is another technique. Instead of adding and dividing by 2, you do some things with the Euler number, and you use some exponentiation, and that's another way of averaging things out. But in principle, it is doing an average. That is what it's doing. Exponential averaging is something that I covered in my channel if you're interested in the mathematics of that. I was using that not for an EQ, but for calculating RMS, to calculate the power of a sound wave, which is something useful for things like compressors. So I have a whole series in which I compute that value in different ways, and one of the ways is an exponential average, and I show you the formula for that and explain how it works. But let's not get too complicated with the math. This is simple arithmetic. Add and divide by 2. Bam. Simple effect. Okay. And in principle, so I was talking about the principle of how ReaFir works. Goes from the time domain, does a fast Fourier transform, gets to the frequency domain, multiply, blah, 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 manipulate, go back, inverse Fourier transform, and construct the waveform back. So that's the principle of an EQ that does fast Fourier transforms. The principle of these EQs that we use every day, the EQs that are the ReaEQ, the Ableton EQ, all of those EQs, they work in this way. They all work in principle like this. You look at the current sample, you look at the previous samples, sometimes not only the previous one, but the second to previous one as well, and you look at just a small window of samples. You do some weird computation to calculate their average or to manipulate them in some way, and you spit out a new value, and that's how it works. That's all it does. So we could look at the previous sample, but also the previous to previous. We could do a nice trick in which our current computation feeds on itself. So we have not only the samples, but the results of the previous averages as well. And then we could use the average to compute the next average. And if you start using an average to compute the next average, you're starting to approach the exponential averaging that Bo was talking about. And if you want to understand the principle behind the exponential averaging, you will need Euler number and you need some exponentials. But if you just use the previous averages to compute the current average, then you won't touch the Euler number directly. You'll be doing an exponential averaging nevertheless. So the mathematics of this is super interesting, but in principle, it's always this. Take the previous samples, compute some averages, and use a formula. In our case, the formula is literally just add and divide by 2. But as you want to do more complicated things, like you want to manipulate how much you are attenuating and where you are attenuating, all those things are just numbers that you plug into this formula. And the more you want to manipulate, the more complicated the formula gets, but it never gets too crazy. I mean, it's going to be at most like 5 to 10 lines of code. And then it will be like, whoa, it will be a super powerful EQ. If you want to implement like ReEQ or Fab filter, it is 5 to 10 lines of code. So why do you pay hundreds of dollars for this? For the user interface. And they all use the same mathematics. Yeah, so we did a low pass filter. Do you want to do a high pass one?
I had a question before on that. So this previous sample, we're just saying it equals to SPL0. So the reason that it's grabbing the previous sample, is it just because of this order? So like SPL equals 0 in this line is previous sample, and then right here it becomes the next sample kind of deal? Okay, cool.
Yes, exactly. And that's why I was getting mixed up in the order of the statements, because you have to get them in order. Otherwise, you risk, if we had the last two lines reversed, we would be changing SPL 0 before we could grab it. And so we would effectively be computing one of the things where the previous average affects the next one. But do you want to try it? Reverse the two lines. Let's see what it looks like on the spectral analyzer. And what we are doing now may be an exponential average. I don't know.
I saved it.
But save that.
Seems like it went back to, oh, it's doing a slight amount of cut. You see it?
Yeah,
Very interesting. Yeah.
Cool stuff. And you can play around with these formulas. And now, can you play around with this in any way? Yeah, pretty much. But there are some formulas with some numbers that are kind of cool. Because there is this thing where if you have an average that feeds on itself, you risk... remember how we had an example before where I was adding a variable, I was adding 1 to a variable, it was just counting the samples. Yeah. Remember how I did that? If you're not careful, then your average may be adding up and then it will blow up. Right? So that has a name, it's a mathematical term, it's called diverging. And your filter may diverge. Effectively, it will sound like crap, it will blow up your speakers, and it will make everyone sad. So you can play with these formulas in any way you want, but there are formulas that don't diverge ever for any values you input, which is a nice property. Our formula right now has this property. Cool. It does not diverge because we are not feeding the average onto itself. I guess we are because we changed the lines, but we were not. So Bobs is asking, I don't understand how it averages, but I will learn. So what is happening is just the current sample plus the previous sample divided by 2. So if the current sample is 0.1 and the previous is 0.3, you will get 0.2, which is just add and divide by 2.
It's kind of like saying, so that's how it's averaged. I got 95 in my first exam, and I got 99 in the next exam. So what's my average score? It's 95 plus 99 divided by 2, which is 97. And we're just doing this to crazy high decimal numbers. Also, hello, Tormi, and thanks for the nice compliment. Means a lot coming from you.
Yeah, so reverse the last two lines so that they are doing the right thing. You already did. So, yeah, so that is fine. So that is a low-pass filter. So we are taking things that are changing at a fast rate, a high frequency, and we're smoothing things out. Can we see the oscillator for that? We may be able to tell visually that things are moving more slowly. I'm not sure, but we may.
I guess I'll A/B it to see the difference. Yeah, we'll see. Yeah, we are seeing some change.
It's slightly more regular, isn't it? It moves more slowly, it seems. Yeah, so that's a high cut filter, a low-pass filter. But what if we want to make things move faster? What if we want to do a high-pass filter? What if we want to cut the low end? All we got to do is make things move faster, right? How do we make things move faster? Well, instead of adding and dividing by 2, what if we subtract and divide by 2? We still want to divide by 2 because our range is between -1 and 1. So if you don't divide by 2, you may get 2 -1s in a row, and you would end up with -2, which peaks, it clips. So you don't want that. But if you subtract and then divide by 2, things that are close together, when subtracted, they will move further apart. And things that are far apart, when subtracted, will become closer together.
So cool. So should I do now SPL 0 minus previous sample to do that, or doesn't matter?
Do previous samples minus SPL 0. I don't think the order matters. Boy. So save, and you see, Now it is a low cut or a high pass filter. That's it. So we started this episode with some simple manipulations of the samples, like multiply the sample by a constant and you get something louder or quieter. And now we are doing, again, simple manipulations of the samples, just adding things up, dividing and whatnot. But now we are working on the time domain. We are just manipulating samples, no FFT, no fast Fourier transform in sight, but we are affecting the frequencies. And we are not affecting much the loudness of things. The loudness is going to be different because we are taking some of the low end, so the power there will go down. So the loudness is not constant, but we're not changing the loudness too much. The values can still go from -1 to 1. So the power pressure of the waveform is going to be relatively similar, but we are changing things in the frequency domain by manipulating the time domain, which is like mind-blowing when you get your head around it. Oh, and Bob's is saying that the problem is with the idea of -1 and 1. Yeah, it gets confusing, like how -1 minus -1 becomes 0, I guess. So it is kind of weird to think about this. But yeah, there you go. So this is our very, very simple EQ. It is both a low pass and a high pass. And as I said, this is like a filter. But if you put a series of filters in a row, you end up with an EQ. And I think that we need to wrap up now because it has been a long time and I need to return to my family. But what we can do the next time, if you want, is to do a bandpass filter, which is just another one of these formulas. And we can get our heads around how it works. And then we can do some other kinds of filters. And then maybe we can look at the real deal. We can look at the mathematical formulas used by Ableton Live, ReaEQ, all those guys, and we can implement them because it's just mostly a matter of writing in code the formula, and we can do a production-ready filter if you want.
So I guess if anybody has any kind of final questions for Leandro, now's the time to ask it. And yeah, as always, this was awesome. I really just like look forward to my Tuesdays now. This is my new life purpose. So this is really fun. And I guess next week is the first Monday of the new month. So I'll be doing another like edited version of our tutorials where I'm gonna just collect everything that you taught me and make like a 15-minute video on it. Yeah, so maybe I'll ask you for some stuff for that. And any last questions? Oh, thank you for subscribing, Bobs NY. Big appreciated. Any last words from you, Leandro?
I mean, you said that the EQ was the hard thing to do. And look at that, it's 3 lines of code. How long did it take us to write? A couple hours, but it was 3 lines of code. I promised that it would be simple.
And now once we know this, I feel like moving forward, like I'm really glad you gave us the backstory because it just answered additional questions in my head. So yeah, that's really cool.
Yeah, thank you for having me. Thank you everyone who was in the chat watching us. It is always a delight to talk about digital signal processing and to write things in ReaFir where you can iterate so fast. There is no like C and C++, you have to write something and compile and wait. And in ReaFir you just save and whatever you are running keeps running and just changes. I think it's excellent to prototype these sorts of things. And I have a lot of fun doing this and it's fun to share this with the world. So yeah, thank you all. I see you next time. I suppose next Tuesday.
Yeah.
Is that right, Arya? Yeah. Okay. Yeah. And I think it's Jamsey who is suggesting to put a slider for the cutoff. Yes, it's something that we can do. We could have a slider, and then the slider would produce a number, and we feed this number into the formula, and we can change the cutoff of this. And how do we plug this into the formula? It's not that complicated. We just multiply the previous sample by that number or the current sample by that number, and that will have an effect on the cutoff frequency. Can you go ahead and do that? Take the sample frequency and multiply by maybe, let's say 1.5. And let's see the effect that that has on the shape.
You're talking about this guy? The previous sample?
Yeah, that works. I was thinking about the formula, so average.
Okay.
On the previous line, delete what you wrote, go to the previous line, and where it says previous sample, say previous sample multiplied by 1.5.
Multiplied by 1.5. So then do I need an extra bracket?
Not really. Multiplication has a higher precedence,
okay.
so you don't need the parentheses. So now you save, and now the curve, the shape is more gentle. It's still there. If you A-B, you will see it, but it's more gentle. And that's because we are saying, I want to take more in account the previous sample. So I want things to move. I guess we are subtracting. So we are doing a high pass. So we are saying, I want things to not move as fast. You are taking into account the previous sample. So you are making things not move as fast. And if you increase this number, then you have a different slope to this. And you can play around. You can multiply random numbers by... That is loud. You can multiply the sample 0 as well. You can add instead of subtract, and that will give us a low pass, as you saw. So you just start plugging numbers in there, and you will have different effects. And you can have sliders associated with these numbers. And if you know what the numbers are and how they relate to the frequency, which is part of the mathematical magic that goes on, you will have different things. So yeah, we can do that next time. We can have different sliders for all these different parameters in the formula.
Yeah, all right. So adios, everybody. See you next week. Take care of yourselves.
Yeah, take care. Bye.
Okay, very successful stream, I